Thank you. As I'll talk about a short extension of framework I introduced last year, where we tried to put a domain-independent planner and a hybrid system together by the use of a PDDL interface in order to, yes, control our hybrid system. What do we mean by that? A hybrid system, from our perspective, is a system which has logical states and numerical states, and some of the numerical states are fluents which evolve along a continuous dynamics. And so here, the system has we have several options to measure our states. We have several sensors which have made some constraints, so maybe we have to have some illumination conditions to measure our states or some other constraints. We have a set of controllers which can change the dynamics of our system, and we have several actuators which we can use to act on the dynamics of our system. So this is basically a switch system, and we discretize these system or each mode of the system to a discretized action of the duration delta I. And this is a thing we can model into PDDL 2.1. And then we can start to use a planner to string together such actions to connect an initial hybrid state with a goal state, a state satisfying some goal conditions. So this is the basic idea. And once we have found such a plan, we can use this plan to translate it back into an input signal for the hybrid system and into a switching strategy of our hybrid system. So where is the need to extend the framework to uncertain numerical state information? Well, let's assume that this is a timeline, and this is our initial state. We usually think that this is really, that we have really exact knowledge of our state initially. But in fact, that's not true. In an autonomous system, a state is usually a result of a measurement, and the measurement is always uncertain. So we have more like a continuous probability distribution around our numerical states. At the same time, planning is a forecast of future numerical state. So we predict future numerical state by the use of this uncertain initial state. And so the uncertainties in our knowledge grows. So for instance, if you're uncertain about your current velocity, you are really uncertain about the future position. Yeah? So this is one interpretation. And you cannot be sure if in the end, if you've applied your plan, you really in the state satisfying the goal condition. At the same time, it's even worse, because planning is more or less a feed-forward control. Yeah, we have an idea what to do, we execute our plans, and of course we cannot model the real world completely in our PDDL model. That means when we execute our plans, the real world acts like a disturbance during the plan execution. Additionally, if we use an actuator which changes our numerical dynamic states, they are also imperfect, and that additionally increases the uncertainties. And in the end, we have both. We have uncertain initial state information and disturbances during plan execution, which may lead the dynamic system into a state which does not satisfy the goal specification after the plan execution. And that's why we would like to handle such uncertainties in the planning process. So I'd like to answer two questions. Can we handle these uncertainties during planning, and does that lead to more robust plans? Robust plans by the meaning that if we have an uncertain initial state information and disturbances during plan execution, that the plan will in any case lead to the goal state. So the good thing is that we can use all the work we've done so far. In the domain predictive control framework, we assume that we have a current state which is equal to the true state. We have a fully deterministic dynamics. We have exact measurements, and the planner can plan a feed-forward signal or a closed-loop signal by switching in between controllers. If we extend that to the uncertain numerical state informations, then we have additionally a random variable E, which is Gaussian mean. We have Gaussian-wide process acting on our dynamic equation over here. We have uncertain measurements. We have a Gaussian-wide process acting on our measurements, and in the end, we would like to give the planner the opportunity to act on the uncertainties by switching on a controller which really acts on the errors. So, if we want to account, if we would like to account errors during the planning process, we have to bring that somehow to the DDL domain. And if we sum up the equation of the previous slide, we get this equation of the dynamics of the error. It's basically combined by the error propagation, the induced sensor noise, and the induced actuator noise. And the problem here is that we cannot precisely predict our error because SE is a probabilistic variable, N is a Gaussian-wide process, and W of T is also a Gaussian-wide process. So we don't know what is happening in the future. But what we can do is we can try to propagate such an error covariance metric through our dynamic system. And a nice graphical interpretation is that the error covariance is basically a region, a confidence region around our future expected numerical state. It contains the true numerical state with a certain likelihood. So up to now, an action looks like this. We have the solution of our planned dynamics, the discretized dynamics, and an inhomogeneous solution if we really provide an input signal. And we have some preconditions, and the numerical effect is then just the discrete evolution of our state. This is expressible in DDL 2.1, and if we want to propagate the error covariance matrix, we have to solve this equation here. I don't want to go into details here, but it's basically composed of the propagation of our covariance matrix, the induced actuator and the induced sensor noise, and we don't have to solve this equation during planning. We can do this in the pre-processing step. And then our future covariance matrix is basically the old covariance matrix multiplied with the propagation and added with the cumulative actuator and sensor noise. And this equation here is also expressible in PDDL 2.1. So planner can then choose and string together actions out of our planning domain to connect an initial state with a goal state. And up to now, the planner would have been done here. This is a numeric variable, and this is the time to future. And the planner has knowledge of these red dots here. These are the expected future numerical states. The planner would be done here because, yes, the state is part of our goal region. But in fact, there's a certain probability here that the plan fails to reach the goal region. And accounting for uncertainties, the planner tries to fit the whole confidence region into the goal area, and this is then what we call a robust plan. I have a very exemplary result I'd like to show you. We asked, can we apply this approach to a docking scenario or a rendezvous scenario where we have a spacecraft orbiting around on a lower orbit here, yes, and we have a spacecraft over here on a higher orbit, and we like to get a switching approach strategy through our target spacecraft over here, so we can reformulate to a linear differential equation, and we have this frame over here. We initially here, we would like to be there, and this is our planning task. And the interesting was here that we get two totally different approach strategies if we account for uncertainties or if we do not account for uncertainties. So where's the difference? How to connect the initial state with the goal state? Well, we have a closer look at the goal region, which is this one here. We see that there are some, I hope you can see that, it's grays and lines. This is the planned evolution of the states, and the grays and lines are the perturbated, are Monte Carlo simulations of the perturbated plan execution, and we see that some realizations here really end up in the state which is basically the prohibited area over here. So we have some probability of a collision here and here. If you account for the uncertainties, the planner tries to exploit the system dynamics in such a way that the whole confidence region fits into the goal region, and yes, tries to find a robust plan. There's another interesting detail of the paper, I think, well, where we can switch in between error state controllers. So if the uncertainties are too large, we don't have the possibility to exploit the system dynamics to reach our goal robustly, we can switch on error state controllers, which then really actively reduces the size of the error covariance. And this is actually a very interesting aspect of the paper, to switch on error state controllers indicate that the errors grow too large. Yes, this is already is a summary. We have to the cost of the error covariance computation, which are basically n squared plus n divided by 2 additional numerical variables in our planning domain, we get robust plans which reaches the goal state despite of initial state information, uncertain initial state information, and despite of actuator and sensor noise. And we can achieve that goal by intelligent exploitations of the dynamics and by triggering on and off in between different error state controllers. So in the end, I would like to say that all the methods I use are very well known in control theory and especially in stochastic filtering. The contribution is here to bring that methods to planning and to the domain predictive control framework. Thank you.